Welcome back to the second video. In this video, we will be defining what reaction rate is, as well as looking at different ways that you can measure reaction rate in the lab. So hopefully after the first video, I have made the point clear that reaction takes time. Every reaction takes time. And some reactions take a very long time, such as these two. And this is to our advantage that it takes a long time. This is rusting. I think this doesn't really happen unless you you leave it for a very long time. Like spoon these days will not rust like this. Some reactions are really fast though, and sometimes you want to slow things down. um, Before you ask, we're not going to do that in the classroom or any of the other reactions. Please don't burn anything down. This looks like a scene from Carrie. Anyway, so you can define reaction rate as the speed at which a chemical reaction proceeds. So we're not that interested in how much product is made overall. We're more interested in how much product is made per second or per unit of time. You normally express reaction rate in one of these following ways. You either express it as the amount of product that is made per unit of time. So we can say 50 mil per second, for example. That's really fast, depending on the reaction. Or you can express it as the amount of reactants that are being consumed per unit of time. You don't actually need to calculate reaction rate in VC chemistry, so a quantitative treatment is not required, but this is a ratio that normally it is represented in. So it's the amount over a time interval. Okay. Now, in order to measure reaction rate, there are a range of methods, and it really depends on the nature of the reactants and the products in the reaction. I will give you a few examples in a second. But I think the main idea here is that you need to make sure, if you want to actually measure the speed at which something is happening, that you record either the change in the amount of product or the change in the amount of reactants at regular time intervals. So you cannot wait until the reactions finish and then just measure the total amount of product. That doesn't give you that doesn't give you a lot of information on rate of reaction. Yeah, so don't just measure the data at the start and the end of the reaction. When you decide method to measure reaction rate, these are some of the factors you can consider. The first one is probably the most useful, is the states of the reactants and products. Do you have a gas being produced? Because if there is a gas, there is a natural separation between the reactants and products, and that's very easy to collect. If there is a change in pH, you could also use that. If there is a color change, and also the level of precision of the equipment available. Do you think it's better to use the scale or the gas syringe or what? Okay, so this is probably the classic method. You can measure reaction rate by measuring the amount of gas product produced over time. So using a gas syringe, and we can definitely do this in the classroom. I think you all have used a gas syringe before, so this is the other purpose of the gas syringe that we bought. So it is suitable if a gas product is formed. So you basically have the reaction happening in this conical flask, and as the product escapes the flask, it is collected in this gas syringe, and then you can record the change in the reading of the gas syringe every 30 seconds or something like that. The only thing that you need to pay attention to or be mindful of is if you're going to collect the gas, make sure that the total amount of gas produced does not exceed the capacity of the gas syringe. This happens every year. People plan the experiment, but they never consider the capacity of the equipment. So our gas syringe has a capacity of 100 milliliters. So make sure that you control the amount of reactant so that you produce less than 100 mil of gas. Otherwise, it's just gonna shoot out. And if you break the gas syringe, no, please don't break the gas syringe. Okay, so let's give you an actual example here. So I have this chemical reaction which is between calcium carbonate and hydrochloric acid, and you're going to produce carbon dioxide gas. So there is a gas produced in this reaction, and that's all we really need. So you can just have the calcium carbonate, which limestone, marble chips, in here, and then the reactant is HCl. So basically, you just need to make sure that you close you close the conical flask immediately after you've added the reactant, and then the gas that is in this case CO2 is going to escape, and then it goes into the gas syringe. And then you can basically plot a graph. So we're going to, oh, look at that. We're going to plot a graph of volume of carbon dioxide evolved over time. Okay, so basically you're gonna start here, and then as you collect the gas, I mean, we're gonna connect the dots, which, well, we can assume that this is definitely continuous. You're gonna have something like this. Okay, so you have a graphical representation of the volume of CO2 produced over time, and essentially the slope of this graph, or the gradient, the derivative, differentiation, whatever nice fancy calculus terms you want to use, that is going to be a representation of the reaction rate. So gradient or slope of graph, this is going to be the reaction rate. So if it has a higher gradient, then the rate of reaction is faster. Okay, now this is a very distinctive shape, and I know this one say mass, but you can also go with volume. Actually, I don't know how to calculate the mass here, so let's go with volume. So the slope of the graph depicts the rate of reaction. The steeper the slope, the higher the rate. And even within the same reaction, you can see there is a change in the rate of reaction over time. So at the beginning, this part, this is the initial rate, and this is always going to be the fastest rate in the chemical reaction. And the reason for that is because you have the highest amount of reactants around here, so the collisions can occur at the highest frequency. So you can have a fastest rate. So the slope is the steepest at the start of the graph, and that's your initial rate. And as the reaction proceeds, you can see that the slope represented here by the gradient of the tangent line is decreasing until you get to this point when you essentially have a horizontal line being the tangent line. And this is when the curve reaches a plateau. I think I spelled it correctly here. This is when the rate is 0, or the reaction has stopped, and you don't see any increase in the amount of product anymore. So it's just a constant. So you need to understand this shape going from very, very high rate at the start of reaction when you have a lot of reactants, and then gradually decreases. So the rate of reaction gradually decreases over the course of a chemical reaction until you get to a point when the rate is 0. There is another way. Well, we're going to go through a few more ways to measure reaction rate. So this is still gas collection, but this is by water displacement. And this is suitable if the gas product has low solubility in water. So you don't want to use this for anything that actually dissolves in water really well. So basically what we have is we have the reaction on this side and on the other side. So this is very similar to the gas syringe method. But on the other side, you actually have a water column, and then you have, we'll have this in the lab. We can do this experiment when we get back. Is that as the gas is produced, it's going to gradually replace the water in this. I think we actually use just a measuring cylinder and then have it upside down. And the volume of the gas can be assumed to be the decrease in the volume of the water over time. So the gas is going to gradually replace the water in this column. This is why it's very important that the gas product has a low solubility in water. Otherwise, it's just going to dissolve in here, and you don't have a correct representation of how much gas is produced. This is another method also used for reaction that releases a gas, but instead of measuring the amount of product being formed over time, this one is measuring the amount of reactant that is consumed over time. So basically what happens is if there is a gas product, it's going to escape the conical flask if you don't have a cap on it. And if it does that, it's going to decrease the mass of the reaction mixture over time. So you just put the conical flask on a scale, and then you pour well, I'll show you how to do it. But basically you can measure the decrease in this flask over time, and that is an indication of the amount of product. Okay. The only thing is you have to make sure that you put a cotton wool on here so that only gas escape, because I'll show you this in class, but some reactions are really exothermic and it actually releases a lot of heat along the way, and then you have water being evaporated. So you kind of want to make sure that it's just the gas that comes out. So you can either collect the product or measure the decrease in mass over time and then assume that that decrease comes from the gas. So that's three main methods. I don't even know. Oh, okay. Yes, so lump of limestone, this is the same reaction, but if we use the mass loss method and I need to plot the graph, it will be a mass bigger over content over time. It's going to look something like this. So it will be the opposite of the other curve, just because this is the mass bigger in content, so it should decrease over time. It should start at some point and it's not going to end at zero, which sometimes I see, and it's like it's ridiculous because you always have a mass of the container, so it's just going to be a reflection of the original graph that we had before. You can still see that there is the slope gets less steep because there's a decrease in reaction rate over time. Okay, some other ways to measure reaction rate. This is to measure reaction time, and this is not going to give you the instantaneous rate of change of the reaction over time, but if you can't do anything else, it's not that bad of a method. It's just a lot of time the reactions happen so quickly that you like there's so much error in measuring reaction time. So the example is if you have this chemical reaction that produces a color, basically you're going to measure how long it takes for the color to make this cross that you're going to put underneath the conical flask completely disappear. So it becomes the solution essentially go from transparent to opaque here. And this is the time taken for reaction to change color. If you have a faster reaction rate, the reaction time will be shorter. Of course, the issue here is you can't really draw a graph and then look at the gradient of the graph as an estimation of the reaction rate. You can't really do that for this method. There are some other methods that we don't have the equipment of, so we probably won't do in class, but maybe it will come up in a question. So you can measure the change in electrical conductivity. You can read this yourself, but basically if ions are being produced, then the solution will have a higher electrical conductivity. And if you can measure the amount of ions in a solution, that gives you an indication of reaction as well. Similarly, you can measure a change in pH. We do have a pH meter. It's just not very sensitive, and especially if there is a change in the pH over time, I don't think it will be able to pick it up really well. But maybe we'll try that when we come back. Oh, we do have this machine actually, but nobody remembers anything from colorimetry from last year. But essentially, colorimetry is when you measure or estimate the concentration of a substance based on the amount of light that it absorbs, and also based on the different colors that the solutions have. I'm just going to let you read this yourself, but basically you can use a colorimeter to estimate the amount of product in each of these based on its color. Is that it? Yeah, that's it for this video.